let's suppose n we have given is 3 and the ages we have given is what? Let's suppose we'll start from here. The first age is here, we'll take from here, give me 1 second. The first age is what? 0 is u, 1 is v, s is 1 and must is also 1. It means this is must. Then another we have is, we can take what? 1 2 1 1. This is also must. Let's take another one, 2 0 1 and 1. We can say that it means all are must use, right? And k we have given is nothing but 0, right? So if we'll form this, so from 0, the 0 node, right? Not like this, we make 0 like this, right? So from 0, if you'll take the strength is what? 1. See, the strength is given 1. We'll say that, and the node is, another node is 1. So if we will take node 0 and 1, right, these two, right, it means from 0 to 1, this is 0 and this is 1. The strength is how much? 1. Let's take 1 and 2. So this is 1, we'll take 2 here. Can we take? What is the strength? We'll take the strength here is nothing but 1. This strength is 1. Now take 2 and 0 from here to here. What is the strength is here? It's also 1. Can we say that? Means we have a strength. These are the strength that we have given, correct? And these are the strength, these are the nodes. So if we will make this graph, right? So if you observe here, there is the spanning tree. It is impossible. It's impossible spanning tree, is it, right? Because all the 3 edges here must use. We are using all our must use, right? This will form a cycle because we use all of them and it forms a cycle. And you can only use how many node? N minus 1. You can see, right? How many? N minus 1 edges we can use. You can only use n minus 1. That is what? How many we have given? N is nothing but 2 minus 1. 3 minus 1 is 2. Sorry. N is given what? 3 minus 1 is 2. Means maximum 2 edges we can use. We are using all of them, right? So at least 1 should not be used here. So you cannot pick all of the 3 edges that we have given. If you will use that, it means no valid tree will return as a 1. So what we will return? We have to return minus 1. If there is no valid tree is there, it is not a valid tree. This is not a valid spanning tree, right? In that case, we will return what? Minus 1. If it is impossible to connect all nodes, saying that, right? And so we'll return what? Minus 1. It means what we are doing, we must connect all the nodes, right? We can use n minus 1 edges. Some edges must be used or some cannot be upgraded. Others are optional and can be upgraded at most once, right? You are allowed at most how many times? You are allowed at most k upgrades total. So what is our total job? Total job is to choose the best edge to make the first tree such that the smallest strength among all of them is as large as possible. Correct? So let's talk about the intuition of this program. Is this problem, how we are going to solve this, right? Means we have given what? We have given a graph, right? And there are some edges must be included in the spanning tree, right? And some are optional that can be upgraded, right? And the strength will become what? Double, right? And spanning tree will connect all the nodes with n minus 1 edges. Means there should be no cycle should be there, right? No cycle should be there, correct? And we want to maximize the minimum strength of each edge in any valid tree, right? Means the minimum strength of each edge, right? We will find, and that should be maximized. Means we have to maximize the minimum strength of each edges in a valid spanning tree. Sounds like tricky, right? But still it is easy. So we have to find the best, that is called maximum possible minimum edge, that is a weight in the spanning tree, right? And that gives us a edge constraint and a limited upgrades. So this is a best for binary search over the answer, because if we'll use a spanning tree which is possible with the minimum edges, right? Let's call it x, we can say. So the minimum edge strength is x, then it is possible for any smaller x, that is x minus 1, x minus 2, and so on, right? So we can apply the binary search to find the large such x, right? It means if we want to implement, what will be our approach? Very first we'll use binary search. We'll use binary search so that we can search the maximum possible minimum strength from 0 to 2 into max edge strength, we can say that. And then we'll go for each binary search candidate, that is called, let's suppose we'll give the name min strength, right? If we'll take the min strength, which is a candidate, right, of the binary search, right, for each one, so that we can check, can we build a spanning tree? If we can build, then if we can build it, right, can we build it so that all the edges in the tree have the strength? What is the strength? Should be greater than this minimum strength, right? And then we'll use there is a concept of you can say union find, right, to use this, right? We will use that, how to find that. Okay, so let's understand what I'm trying to say for the minimum strength, right? Okay, so very first, let's suppose what happened for each min strength, right? If we'll take the min strength, means let's suppose if we have must at I, right? If includes must at I equal to 1, it means this should be must be in the tree. And if the cycle is there, if it causes a cycle, will return what? -1. For each optional one, if it is optional, that is must at I is equal to 0, correct? For each optional is where must at I is 0, the strength that we are talking about, if we'll check if S strength, that is S, right, if it is greater than equal to mean strength, if it is greater than the mean strength, it means we will include the edge directly, correct? If this is the condition, so the first condition, it should be optional, right? If it is optional, means must is equal to 0. So if the strength is greater than equal to the mean strength, means we will include this into the edge directly, right? If the strength S into 2, we are multiplying, right, means we will become what? Is each upgrade become what? Double. It means if it is if the double is greater than equal to the mean strength, another possibility is there, right? So the mean strength, if it is greater than, means we have to store it in a list with the upgraded candidate, we can say that, right? Then means the very first was if m equal to, if the must is equal to 1, it means this should be in the tree and it should not create a cycle, right? And it should not, if it is causing the cycle, it means it will return -1. If it is must is equal to 0, we'll check two things, the strength we will check, and after the upgrade we will check, because we have given k also, that is why we will take what? Upgrade, and we'll check this condition. In the third, let's suppose what we will do, we can upgrade, we can use upgrade on the upgradable candidate, that is this, to connect all the component, okay? And then we'll check, what we will check, are all are n connected? Are they are connected? If it is connected, right, then we'll check it return true. If not, for the min strength, otherwise return false. Okay, so let's go to the code and understand the code here. So the question was given what? We have given n, we have given n number of nodes we have given, right? N number of nodes we have given, then we have given what? Ages we have given, right? Where ages we have given is u, v, strength and must we have given, right? These things was given in the ages, at each ages. It means if the number of nodes we have given and list of ages we have given, the question was asking us to build the spanning tree, right? We have to build a spanning tree who's having exactly how many? n-1 ages, correct? And these n- ages should be connected to all the nodes, means n number of nodes should be connected without forming a cycle. And we want to maximize the possible value of the minimum strength among all the given edges in the tree, right? And we can perform the upgrade at most the k optional edges where must we have given is equal to 0. So we will upgrade it and will multiply its strength, right? Whatever given, means we will do the double of the given strength. This strength should be given if it is 0, right? If it is 0, just multiply by 2. The strength will become double. Understand? So what we will do? We have the union find class, right? We will create a union find class, right? So this class will help us, right, as a core helper to build the spanning tree using the DSU. Remember DSU concept? If not, so DSU is a disjoint set union, right? Disjoint set union, right? If you are following my FAANG preparation series, next I will use the graph where I will discuss about the DSU and we'll go for the basic questions. I have also already uploaded the graph problems, right? If you'll go through the graph playlist, you will see the DSU. Okay, so DSU will help you to build the spanning tree, right? We will build the spanning tree using this DSU, means disjoint set union. Okay, so why we will use the DSU concept? Understand why we will use the DSU here, right? So DSU will make us all the connecting that we will be sure to make sure that we can say to make sure that we are connecting all the nodes, right? All the nodes we are connecting and we are avoiding the cycle, right? First of all, it should connect all the what nodes, right? For the purpose is to use the DSUs to connect all the nodes. So whenever you have the concept of understanding that all the nodes should be connected, just think that the basic concept DSU, right? And you will check that to be sure the nodes are connected. To check all the nodes are connected, we will use the DSU. And another concept to check, it should avoid what? Cycle, right? If it is from the cycle, means this is not also a spanning tree, right? So to check the connected nodes, to avoid the cycle, and we have to check also the merge, right? Because after the upgrading we have to merge it, right? So merge only what? Unconnected, when must is equal to 0, unconnected components. We can say that means when we will use the DSU, when we have to find the connected nodes, avoid cycle and merge only the unconnected components. Understand? So the very first step is to do is define the very few things. What are the things up there? Define the parent, right? So when we define the union find, means we will use what? Union find n, means in the main class you will use, in the main method, what you will do? You will do union find method where you will use this constructor and will say new union find. You can say union find and you will pass what? The n number of nodes. So this union find object will be initialized, right? Then the next we should use what? We have to define the very first, you have to define union find class like this, and you have to prepare the object, right? You have to pass the number of nodes, so your object is ready, right? This is called for the initial steps when we will call the method. I'll show you, don't worry. Then we'll define another method in the main class, that is our min strength, right? Min strength that we are talking about. So we have to find the min strength. It means we have to take the infinite value. What is the infinite value in Java? We'll take integer dot max value. We can take integer dot max value, correct? Then there should be a int age count. We'll take a age count equal to 0. Understand? So we want to create, the very first is create what? The object, right? Object of what? The union find object, correct? Then we want to track the minimum must strength. To find the minimum must strength, we'll use minimum must strength, you can say minimum must strength we will use. So if we have to define, we have to find the minimum strength, you will take infinite value. In Java we will take integer dot max value. Then we will use what? Age count. To track the age count, we have to define it, right? So that we will understand how many count we have for the must ages that are needed, right? Means we have the must at I is equal to 1. So we have to count all those year, right? Means we have to count how many must use ages are added. Understand? So understand how we have to define, right? The very first initial step we need to do, create the object, define it. You will take the min strength, right? And then the age count that we have talked. Then we will use, we have to add all the must use ages first, right? And for that we have to go by one ages we will get from the ages, right? Means we have to iterate over the ages, so that we will add all must use ages first. Let's call it, we will get u from at 0, v at 1, strength at 2, must at 3. We can get it. Or so this is will having 4 attribute at a time at each index, 0, 1, 2 and 3, right? Because this is array, so index will start from 0 and it will go to 3. Means each age contains u, v, strength and must, right? Then we'll check the condition, right? We have to add all the must use is, right? So must is if equal to 1, right? Means that is we have at age 3. If it is equal to 1, it means what? It should not form what? Cycle. So we have already created union find dot union find method, union find class that contains union method. If you are little aware with the DSU, so this union method will return the union between u and v. So if it is returning what? False, it means it will return -1, because it will say it forms a cycle, right? Cycle form is this, the union between u and v is there, means cycle in must have, right? Otherwise we'll return -1. Then we'll check, we'll update, we will track our min must strength, and the given strength is the max value, right? So the current strength will be smaller, obviously. So you will get the min strength updated. Now min strength is not infinite value. There should be some value that we will have updated in this case, right? And then we'll update our age count plus. Means our logic is for all the must at I, if it equal to 1 ages, right? We will try all to connect them. We will try to connect all of them. So we will pass u and v here, right? So we'll try to connect them. If any of the u and v or any of the a's is coming here while iterating and giving u and v 2 nodes we are getting, right? And if any of the a's forms the cycle, it means we will return -1. I hope you understand, right? This is very critical logic here, right? So if we will try for all the edges one by one by iterating the for loop for all the must at I equal to 1, right? So all those edges we will try to connect them. So if it will form a cycle, will return what? -1. And we will update the must strength, minimum must strength, that can't be better than this, right? So we'll use math.min and we'll update it, right? You can use another way if you have approach. So we will update our min strength here, and then we'll count how many of them are there. So we'll just do count plus and it will be get upgraded. The next step is to, so if the edge count is greater than n-1, right? It means what? This is invalid, because if the edge count is becoming n-1, so a tree with n nodes must have exactly n-1 edges. If it is greater than n-1 edge, means it's an invalid one, and so we'll return -1. Understand? Now it's time to save the DSU states. What are the DSU states? Let's understand here. Okay, so the very first step is to do what? We have to save the base. We have to save the base DSU states, right? State. The first is base parent and the base rank. You just do clone of this. So the object uf.parent.clone, we will clone it here, right? And then we'll use rank.clone. So we'll get the base rank. Means we will use this, right? We will use this base rank and base parent to store DSU states during the binary search, right? So next step, we have to do what? We have to do binary search over mean strength, you can say, right? And for that we have to take left at 0, right at 0. Why? Because if we are taking left and right here 0 0, so we'll start from 0 0 itself, right? And we'll take the for loop, right? For each edges we will update the max value, right? So right and edge at 2, you will get the its right value, right? Because we are seeing the left and right? So right will be at where? Edge at 2, correct? And we will multiply its double. Why we are multiplying 2 into max strength? Because we will upgrade edge that can be formed double, right? So we have to multiply with the 2. Now what we need to do? We will check the logic. You know how to do the binary search, right? So over the binary search, you will find the mid. Then this method we will talk about later. Just think that, can we build this minimum spanning tree? We will build it or not? We'll pass the required arguments. If we can build it, just update our left equal to mid, else right equal to mid -1, and then left equal to 0. If left equal to 0, we'll return -1, otherwise we'll return the left value. So let me remind you that you are thinking maybe, why are you using binary search here, right? What is the binary search is getting used here, right? So we are trying to maximize the minimum is strength in a valid spanning tree, right? So let's say the minimum strength is called mean stability, right? And the value is what we are having the binary search over, right? So why binary search we are using? Because if you can build a spanning tree with mean stability, let's suppose x, right? That we have talked about, right? If we have the mean stability is x, then you can use, or you can build it how many times? X -1, X -2, like that you can build, right? So if you can build a spanning tree with a minimum stability x, you can build also for X -1, X -2, like that, right? But maybe you can build it for X +1, right? Let me show you how. What I'm trying to say, why we are using the binary search, right? Because if you can build a spanning tree with the mean stability, let's suppose mean stability, you know, it is x, right? It means if you can build with the mean stability is x, right, means then you can also build for what, x minus 1, x minus 2 and so on. But maybe you cannot build for x plus 1, x plus 2, right? We can say that, and so on, correct? If you will reduce, you can get it, but if you will not reduce, you are incrementing, right, plus 1, it means you cannot build it. Maybe you cannot build it, you can build it or you cannot build it, but surety is possibility is that you maybe you cannot build it. But if you're reducing minus 1, right, minimum stability you are reducing, right, it may be, it is sure that you can build it, because if you are able to build with the x, right, then you can build with what, x minus 1, x minus 2 and so on. But if you are incrementing, there is chance that you cannot build it. So this property is called monotonicity. If you remember the monotonicity, remember the monotonicity, right? One of the video I have uploaded, right, where you have seen that. Means this property called monotonicity, and it makes a binary search applicable. Understand? And so we will use the concept of here, right? And when we are defining left at 0, right, and right at 0, right, so these things we have to define it, right? And when we are going for all the edges here, right, you are taking like this, right? So there is concept why we are using this right, means the stability we are right is become what, 2 into max strength, right? Because any edge that can be upgraded from s to what, 2 into s, right, we can upgrade it, right? So when you are upgraded at most, right, the strength will become double, right? So we set right at as a highest possible value of the mean stability, right? So we can take right at 0, but we can take the max, how max highest possible value, how will you get you the right value, and the e at 2 means this is the our strength at 0, 1 and 2. So 2 is at where, and 3, the 3 things we have in the edges, right? So edges at 2 is the strength, so you will get the highest strength in the right, right? So we set the right at the highest possible value, right? And if it is upgrading, you will get the right at here. Understand? And we are trying to find the largest value of the mean stability such that we can build a valid spanning tree. So this is the purpose of our you can say binary search, right? Means we are trying to find the largest value of the mean stability such that we can still build up a spanning tree, right? So let's suppose we have the mid, right, and we are taking what, left plus right minus left plus 1 by divided by 2 we are doing, right? So this will avoid the infinite loop, and we have the standard upper bound of the binary search, correct? Then we are taking the if condition, we are writing if can we build this, right? This method will return what? So this method is a code decision, right? Means can we build a spanning tree where all the edges, strength, original or upgraded are at least at mid, right? We have. If yes, this means the mid is a valid answer, but maybe we can do better, increase the mean stability, right? And for that we'll take the condition, we'll take left equal to mid, means we want to increase the what, mean stability, right, that we have talked about, right? Means if it will, yes, it will return true, it means the answer is valid, right? And it will, the chances of that we can increase the minimum stability, okay? And so we will update the this. If no, it means this means too large, right? The value will be too large, and so the tree can satisfy the smaller one, right? And so go for the smaller one. Let's try the smaller one, right? So we'll take mid minus 1. Understand? Means when the can build will return false, right? Means return true, not true. It means the mid is too large, right? So there is no tree can satisfy it. Let's try the smaller one. So we'll update our right equal to mid minus 1, right? And this is our final step. where we'll check if we could not build any tree, return -1, right? Else return the left, the minimum stability found, that we will return. For example, let's understand here. I know the question, the video is getting bigger, but you have to understand the strength, the problem concept, right? Let's take max x strength we have given. We call it a max x strength, right? We can say max x strength in is. We have given what? 100. We can say that 100. Then right we can take at 2, that can be 100. We'll multiply. So the total right will be at where? 200. Left is at what? 0 we have taken. We can take. So for the first iteration, when we are going here, so mid will become what? Let's call the mid will become 0 left plus right is 200 200 plus 1 we can say. Left is nothing but this, and we'll divide by 2, right? We can say that. So total is 100 by 2 approximately. We can say that 100 total. We can say that 200 by 2 is nothing but 100, right? Now try to build with every edge that has a strength is greater than this, right? Means we want to build now. Can we build here? Means try to build the tree where every edge has a strength greater than equal to the mid, which is 100. So if the edge has a strength, any of this, there are multiple edges with there, right? So any edges having the edge strength greater than equal to 100, right? What we need to do? Try must the first, right? And we'll set the optional edge should be greater than equal to, if it is 100, we will say that this is optional edges, so that we have to upgrade if it is possible, right? If yes, if we can do that, means if yes, we'll say left is at where? 100, and if no, means right we have to reduce -1, so right will become at 99. Understand? Very first we'll find the mid, then we'll check with the can we build it, can we build the tree with the every edge that has a strength greater than equal to 100, right? Then we'll try the must edge first, right? And we'll say now try the edge having edge greater than equal to 100, right? And upgrade others if it is possible, right? Then we'll check if it is yes, let's update left at mid, right? That will do, this method will do like that. And then if else, we'll return 99 for the right. We'll set the right at 99. In the second iteration, give me 1 second, if we will update it, right? Give me 1 second, guys. In the second iteration, let's say it mid become what? 100 this time. Left at where? At 100. Plus we can take right. Right is at where? We can take 99, right? 99, right? So it become what? 1 plus 100 is 199. Yeah, 199, right? We can say that, right? 100 plus 199 and plus 1. We can say that, yeah, by 2. So it will become what? We can check approximately what? 150, correct? 200 plus 100, 300 by 2 is 150. Yes. Now check again with 150, the same thing. Now we will check 150 with 150 here. Which condition? These conditions we will check. Okay. Now check, can we build it, right? Eventually the search narrow to the higher mean stability that works, right? And so on will keep going there. Okay. And we'll update its left, right, if it will form, right? We'll go for all the edges. We know if it is greater than equal to mid, we can form it. If yes, we'll update our the mid at here, right? If not, we'll update our mid -1. So it will keep updating, keep checking this value. Okay. So now understand the can build method, right? We will pass this argument, right? the edges, k, mean strength, base parent, and base rank, right? We will use this. So this method is the main check, we can say that, right? So this method will say, can we build a valid spanning tree where all the edges used having the strength, right, is greater than equal to the mean strength, we can say, right? If the strength is greater than equal to greater than the mean strength, return it's false, right? Because we have to check if it is the mean strength is greater than the mean must strength, means we have to return false. We will not do anything, right? We cannot build it. Otherwise we'll restore the DSU, means we have to again you have to take the UF object, parent, and rank. We have to initialize this value, so we can restore the DSU after must use edges were added, right? That we can say. Now we'll take an upgrades, and you can take the optional edges here. Let's classify the you can say optional classes here. How? Just iterate all of these edges one by one. You get UVS and must is. Check must equal to 1, means we don't need to do anything. If it is the strength is greater than the minimum strength, you just make a union UNV. Else you just take the if it is upgraded, if it is greater than this, means we have to add it here, means we have to check the strength. If it is greater than, right, just add into the upgrades. The remaining is k. To check the remaining, you will go for all the upgrades. You get upgrade U and V. Check if it is not connected. If it is remaining is 0, return false. Otherwise connect it, remaining is minus minus. We will decrease it, right? Then we'll check if root is we will initialize the root, right? And we'll check for all of them. If not equal to the, if any of this is not equal to the root, return false it here, right? Otherwise return true. It means it is connected or not connected, it will give you here, right? Understand? It means what we need to do, once you will come to this method, right, you will just restore the values, right? Then you will take the optional edges, right, optional edges, and we now loop all of the optional edges, and for that you will use this loop, right? You will loop all the optional edges, you can say. You will get UV and strength and must, right? You will check the strength. If a strength is equal to 1, just continue it, don't do anything. Go for the next edges, right? And you will check first if S is greater than equal to mean strength. It means we can directly use it, right? We can directly use it directly. If a strength is greater than equal to after multiplying double the strength, if it is greater than equal to, it means it can be upgraded. Just upgrade it. Okay, so we are collecting all the edges that can help to reach us the mean strength. Okay, now we will using what remaining k, right? So we'll use the upgrades. We'll use the you can say upgrade greedily, right? So that we can take remaining k and we will use the greedily upgrade greedily, right? And so it will you get all the nodes. You will just check the if it is what connected. If it is not connected, you will check the remaining should be 0. If it is 0, return false. If not, just take it. Returning is and return remaining minus minus, right? Means we want to only upgrade when it is necessary to connect a new node. Okay, then this is our final root check. It means we want to make sure all the nodes are connected, right? Only then we have a valid spanning tree, right? Then finally we'll return true or false, right? If the left is 0, right? If left is 0, the condition was that if left is 0, right here, right, is 0. If left is 0, then 3 isn't valid, return -1. Otherwise left is, we return the left. Okay, I hope you understand this video, and if you have any doubt in this video, please let me know in the comment section. I will request you to take a time and subscribe this channel or like this video. If you have any issues, please ping me in the comment box. I will be your journey partner as a support, right? I want to make impact on the couple of engineers so that we can be a part of your journey. You will remember always the expert Honda. So I will request you also, please pause this video and go through the code, overall code, and check what is the complexity there. Write the complexity of time complexity, space complexity. If the complexity is correct, I will give you a thumbs up, and the rest of the people will understand this is the right one. Thank you guys. Thank you for watching this video.